Thank you. So I'm going to be talking today about Elixir's GenStage module and putting it in the context of data processing. So I am Peter Hastie. I'm online as SillyPog on Twitter and GitHub and everywhere else. I've been working at Bleacher Report for about 4 years in kind of a variety of roles. I started as a front-end developer, and after about a year I transitioned to the back end, originally on the data engineering team, and then more recently on consumer services. And you can read a lot about my exploits on our company blog that has a lot of great insight from a lot of the developers on the team. So I have really only been working with Elixir since last year, which I'm sure means people are wondering why I'm up here giving a talk. But the module that I'm going to be talking about has also only been in the language since last year. So there are no experts here, except for James, who may or may not be in the room. He actually is an expert on it. So GenStage is a new Elixir-specific OTP behavior. So unlike something like GenServer, which is coming from the Erlang world, Elixir was built so far only on Elixir, which is kind of a nice win for the language there. It was created by Jose and James Fish. They currently maintain it, and anyone can just add it to their project through the mix file as a dependency, which is a little awkward. When I started this work in this presentation, GenStage was designed to be, or expected to be, part of the main language, but it grew so big that they decided to keep it out and keep it as a separate thing. So I am presenting on someone else's library that I have not contributed to, which is not what I intended. But the good side of this is that now the implication is that anybody can put an OTP behavior up on a hex, which I don't know, how do we feel about that? It's exciting times. So GenStage was designed to allow you to exchange events with back pressure between Elixir processes. And this is a phrase that I've lifted straight from the Announcing GenStage blog post that came out last year, which is a really fascinating read. It gives a lot of great insight into why they created this module. And even though a lot of that blog post is now the documentation for the module, I think it's still worth reading. It's got a great video at the end, actually, where they build a data pipeline. So if this talk isn't very good, you can actually watch a good version from Jose doing the same thing. But I want to unpick that phrase a little bit. What is back pressure and why do you need it? Because normally we don't have to worry about this. When you're working on data collections in Elixir, a lot of the time you'll be working with the enum module or the stream module, and these are both, they make use of synchronous functions. So as a piece of data moves through the streams, as you're piping functions together, each piece of data is fully processed, and then the next one will start. So the back pressure is given to you and built into the system. However, once you switch over to using GenStage, which is built on top of processes, now you're in the asynchronous world, and you do start you have to start thinking about back pressure. Because if you do not have back pressure, what can happen is you'll have a very active process that's producing messages, sending them to a second process much faster than that second process is able to deal with them. So for example, you're reading files off disk and you have to process them, decrypt them, something like that. So as these messages are coming in, they're filling up the consumer mailbox, and there isn't really a bound to this. Prior to Erlang 19, the consumer mailbox could fill up so large that it would take up all of the memory on the machine and bring down the entire beam, which is probably not what you had in mind when you were planning to let it crash. So that has been a little bit alleviated. Now there is a feature flag called max heap size, where as processes hit that limit, you can kill them. But if that happens, then you're going to lose all of the messages that were in the mailbox. So so there's still a penalty there. In contrast, the model that GenStage is using for back pressure is to have the consumer actually make a request of demand from the producer, and it will say, I can handle 5,000 messages right now, send them over to me. So the producer will send those messages, as many as it can, no more than that number though. They'll sit in the mailbox, the consumer will work on them one at a time, and when they're done, the consumer will ask for more, make more demand. So this means that a system like GenStage can be really helpful anytime you have control over the rate of production. So if you are pulling messages out of a queue, or if you're reading files from disk, this can be helpful. If you have something like a TCP server where you can't control the rate that messages are coming into your system, then you will have to look for a different solution there. So this is the example pipeline from the documentation. And before I go into this, actually, I had meant to ask, has anyone in the room worked with GenStage and used it in a project at this point? Okay. Not many people, so I will go into this part in a good level of detail, or I'll try anyway. So the way that this works is that you start to design your applications in stages, where you will have a producer stage that's generating data, and a consumer stage that does the final transform in that data, and any number of producer-consumer stages in the middle. So in the example pipeline that they give in the documentation, you have a producer that's just generating numbers, an infinite number of numbers, in response to demand from the consumer. And then the producer-consumer stage receives those numbers, and it manipulates them in some way. In this case, it just doubles them before handing them on to the consumer. And the consumer has a sleep delay just built into it to simulate the fact that this could be some kind of long-running processing. So because the consumer is the rate-limiting step in the pipeline, if you want to increase the throughput of the overall pipeline, you would have to increase the number of consumers that are available. So you would just spawn more consumer processes there. And this is how they define the setup in the application code, where they are setting up 4 consumer processes to ensure that the throughput is pretty good. So here you have, you're starting 1 producer, which is A, 1 producer consumer, which is B, and then 4 consumers, which is C. And then each of the consumers is subscribed to the upstream B process, and the B process subscribes to the producer. And one thing that jumped out to me here was that there is a lot of boilerplate here. As you add a number of stages, you have to write more code, which, being very lazy, didn't seem great to me. So I created an extension of that example project to kind of explore some of the beginning ideas of working with GenStage. So this is up on my GitHub profile, the supervised GenStage app. And I'm going to attempt to run that now. Okay, so I should have probably made the fonts bigger here. Is that big enough for people to read? Cool. Okay, so yeah, here is my version of the application. This is basically, it's almost exactly the same. There's a small difference, but I don't have very much in my application code at all. I just am setting up a supervision tree here. And I don't have any subscription happening between those stages. And I'm actually going to start at the end of the pipeline with the consumer, because everything really starts when the consumer makes demand. And that happens down here now. So this is the example C module. It's being initialized as a consumer. So this is how you would, this is the other way that you can set up your stages. You set up your consumer, set up any state that it needs to have. In this case, I'm just keeping the pipeline name for logging and the delay to simulate the long-running process. And then the key part here is that you subscribe to your upstream process, and you set the demand here. So in this case, I believe the demand will just be 1. It's just asking for 1 message at a time. And so that demand that we've created as this initializes will be sent, because that's subscribing to the producer-consumer, and the producer-consumer is subscribing to the producer will receive that demand in this very OTP-like manner where you might be used to like handle call and handle cast. Here we have handle demand, which is, this is the new thing that makes GenStage special. It receives that demand and it tries to fulfill it, and then asynchronously sends these events, which would be an attempt to fulfill that demand, back down the pipeline. So that self-subscribing thing was really like my key to getting past all the boilerplate, but it also meant that now that I didn't have as much stuff happening in the application file, and the modules were subscribing themselves, I was able to start exploring what happens when a module dies, and now that it can self-subscribe, can we bring it back up in a supervision tree? And the great thing is that the supervision trees there's nothing different about them. You would just supervise these GenStage processes exactly the same way you would supervise anything. So here I have my supervisor for the downstream stages. So basically I have the producer-consumer and the consumer being supervised. And the key thing to get this working was really, I had to find a way of allowing because the consumer is going to look for producer consumers based on the name, I had to have a discoverable name, but it also had to be unique. So I passed the pipeline name into the producer consumer so that it can build its process name just by joining like pipeline name. So if it was slow pipeline plus the B, so that way when it launches, you just build a new atom from that. And I know building atoms on the fly can be a no-no sometimes, but here we know how many we're going to have, so it shouldn't be a problem. So I will try and run this. I will also make this bigger. Okay, so this is just going to have it has one producer consumer and one consumer asking for one message at a time. And it chugs along, and you see every third or fourth line says fast pipeline with a PID, and then it's printing out an even number because this is the result of doubling something. So that's not very exciting at that point, but that's GenStage in action. Oh, actually, I had a second thing I can show you with that. Sorry. So I was wrong. I forgot to comment out of line of code. So we actually do have two pipelines. So there's one producer, but there are two sets of consumers reading from that. So one is a slow pipeline that takes 5 seconds to process the message, but asks for 3 messages at once. The second one is the fast pipeline, which only takes a second and only asks for 1 at a time. So you can see the effect of asking for different amounts of demand here, because the fast pipeline, every time that writes out, it just writes 1 message. But just about to scroll off the top, there was slow pipeline. Every so often there's a slow pipeline that has 3 messages associated with it. So you ask for 3 events, you get up to 3 events. And then just to show, it worked. Okay, I typed in observer.start. Can't really see it. So here, because everything is supervised now, if I take down one of the pipelines, kill that process, then we get our little error message, but everything chugs along. If we didn't have it in the supervision tree, it wouldn't survive that. And so what's interesting is, the last time the first pipeline worked, printed like 144. Somewhere along the line, we lost 146 because that was in the mailbox when it went down, but it came back with the next message. So you still lose your message, but this time you're only losing 1 message, which is a lot better. And the other thing that's interesting is that the first pipeline, the consumer was PID 162. When it comes back, even though I killed the B pipeline, the B process that wasn't directly the parent of the consumer, it took down the consumer as well and brought that back with the new PID. So that process of subscribing the processes together is also linking them, which wasn't immediately obvious to me. This is up on GitHub, and the way I have that repo structured is that it's I have a branch for each step, so you can go back to like step 1 and see like the world's simplest GenStage pipeline. So if that's interesting but hard to follow during the talk, there's an easier way of running it for yourself. So I'm going to change tack now and talk about some of the data engineering challenges that I was working on at Bleacher Report over the last few years that kind of brought me to this point of thinking about GenStage. When I joined that team, we were supporting a number of legacy applications that had been designed to store specific pieces of data, and this is data that would be just user actions in the app. So if someone reads an article or subscribes to a feed on Facebook, we'll receive those events, and the business analytics team can make strategic decisions from that. And the big problems really were that we had too many different places that the data was stored, an unclear flow of how data moves from one location to another. And the business team really wanted a single data warehouse that they could use to, I forgot to start the timer. A single warehouse that they could use to make decisions from. So we designed a new pipeline that should handle 100 million events a day, although our current pipeline is actually doing 160 million a day. So that wouldn't have worked. I wanted to separate the capture, processing, and retrieval of events into separate applications, just keep it so that it was very clear what state data was at any point, and not have data retrieval affect data capture, which you'd think wouldn't happen, but for one of the applications, we were storing data in Amazon's Redshift database. And if a query got stuck in there, it could be stuck for several hours, and we're no longer able to copy tables out of DynamoDB into there. So tables start to back up in DynamoDB, and eventually we might exceed the amount of capacity we're allowed to have there, which costs us money and stops us from being able to create new tables. So I wanted to make sure those steps were more isolated. Wanted to store events in their original format and not have them put into normalized databases that are answering specific questions. We wanted to be able to go back with new questions for the old data and still be able to answer that, and expose it via an SQL interface for the team. So this is what we came up with, and like the key thing here is that it's very linear, so it's very easy to see like how data moves through the pipeline. Data comes in from clients. We collect it in a Node.js application. The reason we used Node was because we had used it before and we were able to use a lot of the code we had, but Elixir would have been a really great choice here. We write that to Amazon's Kinesis system, which is a queue, a bit like Kafka, that allows us to batch up all these disparate events and write them in batches. We write those out to S3. And then the key thing here, what drives the events through the pipeline at that point is that S3 fires an event. Our Ruby application called Palette will retrieve the file that it got the event about, process it so that it's ready to be imported into Redshift. It can't write it directly to Redshift, so it writes it into a new S3 bucket. The same process happens, and the final application called Forklift will do the bulk upload of that converted file over to Redshift. So the key really is those events coming out of the buckets. S3 can emit events on any change, but the only change we care about is an object being created. And we also only care that it's the new raw data coming in, because when we write the process data, we'll be putting it back in the same bucket, because you have a limit on how many buckets you can have. And so we also restrict by the file name. Those events can be sent through SQS, SNS, or Lambda. And the reason why we chose SQS for this was that we're expecting a pretty continuous turnover of events. So the overhead of spinning up Lambda functions is probably excessive. We also expect that our application will go down. Maybe if I build it in Elixir, it wouldn't have, but we have 9 5s on Ruby rather than the 5 9s. So when that's down, if we used a simple notification service, that just fires messages into the ether and expects listeners to be available for it. So having them on a queue is better there. And SQS also guarantees at least once delivery, so we won't have any files left behind. And the key thing also is that we wanted to ensure that multiple instances of Palette, like if we want to increase the throughput through the pipeline, we'll just spin up more instances. We wanted to make sure that those are not, we don't have 2 instances processing the same message at the same time. And that's also the reason why we even need need the events in the first place. If we were just polling the bucket looking for new files, then two instances doing the same polling are going to end up retrieving the same things. The way SQS guarantees that you're not going to have 2 instances pulling the same message down is this visibility timeout. When one instance of Palette asks for an event, it will get that, and then in the ideal world, it will finish processing it, and then it will go back and delete it. But if it crashes for some reason, or if it just gets stuck, then it will never send the delete. And that message, since it was always still on the queue, it was just hidden. After a timeout, it will just become available again, and another instance can pick it up. So yeah, I'm really going to dive in a little bit to the Palette application. It was originally, I wrote it in Ruby, and it really is just a loop. It uses an SQS polling loop to keep firing messages up to SQS. As soon as it gets a message back, it will block, do all the processing on that message, and once the file has been fully processed and uploaded to the next bucket, the loop will continue and it will start asking for new buckets. So there's no aspect of the application that was parallel, running anything in concurrently. And the way that we were going to scale this, it was actually scaled really nicely on my laptop because I develop everything in Docker containers, and if I want to spin up another one, I can just say Docker compose, give me 4 instances of this. And that's the same process that we would use in production. We run everything on Elastic Beanstalk, so that means that if we want more of something, we just need more instances. It's not very efficient, but it works. And that's really where the one problem that this application had is that because the SQS polling loop is built into each of the applications, as we launch more of them, it means that we're polling SQS more and more frequently, but there's only going to be the same amount of messages, and processing a message takes no time in comparison to processing the whole S3 file. So it would be much better to bundle the request for messages together. And since Amazon charges per request, this can get kind of expensive, and Amazon did really well out of this. So you're welcome, Amazon shareholders. I've turned it off now, so you can see it's so I thought, is there a better way of doing this? And I was just getting into Elixir at the time, and GenStage literally just came out the day I realized that this was a problem, and I'm like, all right, well, I imagine that will do the job. Let's go and investigate it. So I built this application. It's the SQS S3 GenStage app. It has the same thing. You can check it out. You can step through the first branch is the very simple version, and then it builds from there. The structure of this application is it's based on a GenStage pipeline where we have a producer that is responsible for fulfilling the demand from the consumer to actually request messages from SQS. It hands those messages to the producer consumer, which downloads the appropriate file from S3. And then the consumer will, in this case, the consumer just counts the number of lines in the file. But you can obviously do whatever you want to do with it at that point. And the key is that we'll be bringing up more producer-consumer/consumer downstream pipelines together using that supervised method that I showed with the first example. And so because we have multiple consumers making demand, we don't want the producer to block while it's looking for messages. We want it still to be available to get more demand. So the actual job of polling SQS is done by a separate module which just has a loop function that runs as a task, and the producer will turn that loop on and off as demand for messages comes in. I don't want to spend too much time actually like going through the code on this because it got complicated by the end, but just in general, this is the basic structure of the application, pretty much what I described in that diagram. And the way the server works is this loop function is what does the work of receiving messages. I'm using the EXAWS library to interact with SQS. And then the messages come in, and I use Suite XML to parse those out and get the body. The body of the message is the location of a file on it, or is the event that came from S3, which I have to use Poison to parse because that's in JSON. So thank you, Amazon, for your consistency with your serialization there. So if it receives a message, it will send those messages back to the producer. And I'm doing that through here. It makes a call to a function that I've defined, this enqueue. It's doing this. Originally, I was just using like send to send it as if it was a process, because it is a process. But I feel like if you're going to go with OTP and use Gen servers and Gen stages, you should just go all in and define specific APIs and make the relationship between your modules really clear that way. When all of the demand when the number of messages that were asked for have been found, the loop will exit. If it still has more to do, it will wait another 5 seconds and then look again. And that's really kind of the key part of this. The producer is controlling it through the pull method here. If there are any servers looping when more demand comes in, it will just kill those first before it starts a new set. So I have a video of this in action. It's not the most fascinating thing, but it's basically I have no files in my output folder yet, but so there's nothing up my sleeve at this point. Run the application, so it sets up all of the stages. There's a lot of logging in it, just because I was trying to see the order that things happen. And now the server is starting to loop. It's looking for events. It's looking for 3 events because it has 3 downstream consumers. It does this it'll just keep doing this every 5 seconds. There are no events right now. I don't have anything in the S3 bucket, but I'll upload a bunch of files. Each file just has 200 events in it. I probably should have varied the number to make the demo more interesting. So there we go. We've uploaded the events now, and in a second, they've all come through. We've got a bunch of messages into the application, and it very quickly processed them. Well, this is just to prove that they really are up on S3. And the server processed them very quickly because they were very small files, and now it continues looping, looking for more. And now I attempt to check what's in my output directory at this point. Oh, I have an analyzed version of each of those files that just each one should say the number of lines that were in the original S3 file, so 200, which is the right number. I can't believe it worked. Okay, and so from there you just go ahead and fill in all the details. And, I'll leave that as an exercise to the audience. So this part is I feel like this is the key part of my talk. So I used a couple of libraries to work with this. When I built the application in Ruby, I used the official AWS SDK, which does provide low-level features for interacting with SQS. But because it's been around for a while and it's very mature, it also has these higher-level abstractions, like the queue poller, and it makes a good argument for using it. It says it uses long polling to keep your costs down, and it's already built for you. So I thought it makes sense to use this, and it had a very profound impact on the architecture of my whole application, and led to the scaling issue that I mentioned. In contrast, when I built it in Elixir and I used the EXAWS library for this, they don't provide any higher level abstractions for working with SQS. So I was forced to use the functions directly, and in doing so I really had to understand how SQS works. Didn't know anything about that visibility timeout before I started working with this. And I really had to understand how OTP works, how the messages are being passed around, and starting tasks, dealing with asynchronous processes in much more depth than I would have otherwise. I noticed now that the S3 module, when I think I started working with this project, I don't think it had the higher abstractions, but it does now. At one point, those were actually based on GenStage. But I think that's really an important thing to think about when you're building an application and you're using libraries for it. It's going to have an impact on how you design things. And also, I would say, working at that low level, it was one of the most satisfying programming challenges I've had in a long time. And I swore a lot during the process, which I think is a really good sign that learning is happening. So Bleacher Report is a super fast-moving organization, and we're already onto a new pipeline. Instead of managing it ourselves, we now have vendors that we work with, which means I have time to come to conferences, and I don't have to respond to alerts anymore. We're partnering with mParticle to handle the client events. They duplex the traffic to all the different analytics providers. So Google Analytics, we also use Flurry, a few other things. But the crucial part for me is that it also writes the events to S3. And then the other partner who, if anyone hasn't worked with Interana, they're a joy to work with, really great. They provide an analytics API that lets us query the data, and they also have a really lovely web visualization that lets the analytics team play around and explore the data. So before we could really commit to working with these vendors, I had to do a lot of, actually myself and Gratian, who's in the audience, did a lot of technical due diligence with these companies to make sure that they could fulfill our requirements. So one thing that I had to do was just count to make sure that we were getting the same number of events in Interana that we actually thought we were getting on S3. So the events that come in from mParticle, this is expanded. Each file, so each line in the file is a complete JSON object, but within that there are multiple events, each with different timestamps. And I haven't exactly worked out what the relationship between all of them is, but it makes it a somewhat challenging process to get a count on those events. And the way that I chose to do this, we're talking about a pretty large amount of data. I was using the streaming mode on Elastic MapReduce. I don't know Java, and it allows me to work with languages I do know. So this is basically the local machine equivalent of the streaming mode, where you just cat a directory of events, pipe the output into your mapper, sort the output of that, and pipe that to your reducer, and eventually you get your output. So I ran this with I'm only including this Ruby code to show that it is very simple. There's not a lot of room for error here. The mapper just extracts the timestamps, converts them to days, and exports them with a count of 1 for each of those timestamps. And the reducer will then take all those counts of 1 and just add them up for each of those days. It's a very short file there. So everything works great locally. Up on Elastic MapReduce, after 12 hours, it errors with no explanation. And I'm thinking there must be a better way to do this. I'm streaming, I'm mapping, I'm reducing. That all seems like stuff that Elixir is really good at. So the first attempt at this would be to lazy load the data using streams. So this is almost the canonical example of how you would stream a file and do a MapReduce algorithm on it. It's very short, it's very simple, and works nicely. But we have better options than this now. Enum and stream, so where GenStage brought us into the asynchronous world, there is now a module that's built on top of that called Flow. And so while stream builds lazy evaluation, it gives you lazy evaluation over the enum module, Flow gives you concurrent evaluation, so you can take advantage of all the cores on your machine to process files now. And the way that this would work would be you would stream a file into the flow from enumerable function, and then you pipe that into flow flat map, and flow will decide how many mappers it wants to pass that through, and similarly how many flow reducers it wants to pipe it through. And you don't really have to do any thinking about this. The machine knows what to do. And these roughly map to the stages that we know from GenStage. So the great thing is you don't really have to change your code very much to take advantage of Flow. The only real difference here, I'm calling the Flow module instead of the stream module. And we take the initial step is to take the stream and then do the from enumerable to turn it into a flow. But from that point, you're just mapping and reducing again, and the contents of those functions are the same. And this is great because it was about twice as fast as the original Flow version. Unfortunately, it was also twice as wrong. And every time I ran it, I got different numbers. They were always wrong, but they were wrong in different ways. And it's actually interesting that they're only wrong for the larger numbers. The smaller numbers are correct. And that gives a little insight maybe into what sizes of batches of data Flow is working with as it moves things through the pipeline. And the key was that I had missed one line from the documentation, which was to partition the flow. And what that's going to do is set up new stages for reduction and manage bringing all of the state back together at the end. But flow partition is where Flow turns from being a super cool, easy to use alternative to stream to a John Steinbeck novel of documentation, and it's amazing the thought that's gone into it, but there is a lot to digest there. And using partition made the data correct again, but we lost a little bit of performance with that. And this was entirely because of the structure of my data. And so this is another key takeaway where whenever you're setting up these pipelines, you've got to know your data, and the one size is not going to fit all with these pipelines. So what was happening for me was that I would take a file for a certain day. I would send that to multiple mappers, and Flow is setting up multiple reducers as well. But because the key for 99% of the data from a certain day is going to be the timestamp of that one day, almost all of the data goes through one reducer, and we're not taking advantage of the other processes that were being set up. So it was similar to me saying, please just partition it over one stage, which is basically saying, don't make this concurrent. But there's a lot of other functions available in Flow, and I was able to get around the problem by using group by key, since we're grouping by the key of the timestamp. And then I use flow emit to just kind of dump out the state of each of the map stages. So what I'm getting back now hasn't been put together for me, but since it's just a handful of timestamps for the different dates with counts for those, putting it together looks like a lot of code, but it's very simple computationally because it's a tiny amount of data at this point. And we're back down to the good timing that we had before. But we can still do even better. What I had in this previous version is that I have my two files. I pass them into the function one at a time and manage reducing it myself over this. There's my global reducer here. And so the final step is going to keep accumulating that for each of the files. But there is a better way, which is to use flows from enumerables, where you take all of your files, you set them up in multiple streams at the beginning, take all of those streams, pass them into from enumerables, and here my global counter is now just the single map, and I don't have to manage it anymore. So I think it's awesome that Jose has sort of thought about how people are going to use this and work with it. And from enumerables is always faster. Like, it seems like you should never not use it. So for all of the different flow cases I tried, that was the best. So all of the code examples in that last section are in the EXMR module. If you want to take any time to digest that, I know I kind of flew through it. The very last thing I want to talk about is how the EXAWS library was using Flow back in the day. So if you want to see how a real professional programmer would use it, it's that. I think it looks similar enough to my version that I'm not ashamed. Yeah, so it's basically doing the same thing. Here it's downloading files from S3, but it's chunking them and putting each of the chunks through different pipelines and putting it back together at the end. But that is, even though this came out in 2016, this is no longer the hottest, newest way of doing it. Elixir 1.4 introduced task async, which is really perfect for these like chunking or multiple downloads, anything like that. So that's already changed. And again, if you're working with a library, you don't necessarily see this unless you're digging through it for a presentation or something. So yeah, in conclusion, you can use GenStage anytime you want to introduce parallel steps into your programs. It will help you to regulate the flow of data between your processes, and you can and you probably should use it in supervision trees. It doesn't seem to take any extra work, and it is becoming the basis of new abstractions. So if you don't act quickly, you may never get to interact with it yourself, and all the fun will be done for you. So thank you very much for listening. My slides will be online at that location, and there are the links to the repos that I mentioned. So, thank you.
I think we have time for some questions. Go.
What is your current SQS bill?
Current SQS bill. That's actually a very interesting question. So different companies optimize for different things, and Bleacher Report does not optimize for cost. And what I always found a little disappointing when I was on the data engineering team, it kind of became apparent to me through the process that a lot of the really hard problems in moving data around have been solved, and it's become a cost management problem where there are so many solutions out there. The right solution for you is the solution you can afford that gets the work done. And for me, I never got to see what our bill was for anything, and no one ever pushed back to say we should find a more efficient way of doing this. I think that's why we've gone with vendors now, because if we've got the money to build a great solution ourselves, we can pay someone else to make an even better solution. So yeah, at the moment the SQS bill is actually 0 because we have moved away from that system now to the vended one.
So when you were building that, have you looked at actually consuming the messages from Kinesis directly and bypass SPS and S3?
That is an excellent question. So yeah, the question was whether I could read the messages directly from Kinesis and bypass S3 and SQS. So Kinesis is a newer Amazon product, and the API for that does evolve a lot. So I know that the Firehose capabilities of that became available while we were working on the project, which did allow us to extract the data in different ways. But one of the key things is that we really wanted the data to be in S3. That was almost the main goal in some ways, because having S3 as the source of truth for all of the events means that they're in there as a nice sort of human-readable JSON format. They're easy to reprocess if you want to. And our previous version, where we were writing data from DynamoDB directly into Redshift, anytime we wanted to do any MapReduce jobs on that, we had the annoying step of having to extract it from Redshift into S3 before we could do EMR jobs. So a lot of this is really kind of comes down to what Amazon API capabilities are there at any point in time. So for us, we weren't able to read directly from Kinesis to get what we wanted at that point.
That's fine, but like, you can still do the firehose on top of Kinesis and drop it in S3.
Right.
With Kinesis, you get like a stream, right? And you can read off that stream in any position in the last 24 hours. So you can completely bypass SPS.
Firehose and stream are different things.
There is also something I didn't want to get into too much here was that when we were writing data into Redshift, we were putting it in as a star schema, which isn't necessarily the right way to work with Redshift, but we had to do, yes, absolutely. We had to do a lot of processing of the data before we could get it in, so having it move through those different applications for processing was a key thing there.
We're going to have to wrap this up.